Today, we're going to talk about precipitation data, how we collect it, and how we analyze it for frequency analysis. So first, we're going to explore rainfall measurement and estimation methods. We're going to do a little activity in class. We're going to investigate frequency analysis with precipitation data. So this is bringing back stats, and we're using a Weibull plotting position, which you all used last in statistics. And then we're going to utilize precipitation data analysis to estimate design storm depth and duration. We'll do that on Monday, but it's all kind of part of the same package here. So first, we'll talk about precipitation data, and other types of things. We're passing around this tipping bucket, which is on the bottom here. This is a data logger. It can give you really high resolution, kind of second by second rainfall data. We've got a kind of scientific grade one that has all these kind of funky contraptions on them. What do you think those are for? The rain gauge is in the middle. Yeah, it's wind. So it's really hard to measure rain, because if you've ever sat out in a rainstorm and watched it, like, are the raindrops just falling straight down? They're going all over the place, and there can be turbulence. And so the rain gauge itself can create turbulence that would bias the measurements potentially. And so this device is made to basically reduce wind turbulence around it, updrafts, downdrafts, that kind of thing, and try to get a fairly accurate rain estimate. So we can get pretty fancy with these. There we go. So here's what rain data look like. If I were to actually have this is data that I collected using a rain gauge just like this, and it just shows you those little ticks. So we have the units on the y-axis, which would be rainfall depth. That tipping bucket, you just convert each tip to the depth of water that would take to tip the bucket. In this case, 100th of an inch. And then you just add them up. So we can see the vertical bars where we have a big rain event, right? So we had 50 something tips over a couple hours, and then nothing for a long time, and then a little bit of a rain, and then we had a couple big rain events over a couple days up there. So you can take that kind of step time series and turn it into bar graphs. And so if you just say, okay, I'm going to just splice it up and sum everything up for every hour, then I can get this type of thing. So I just get a bar graph showing the depth per hour or whatever time frame I'm interested in. And we call this a hydrograph. Which is just rainfall depth over time. And you can see it says hydrograph right here. Now, this is our way to measure rainfall. We can get a little fancier, and we have rain gauges, a network of them across the country. However, it's hard to run. Like Grand Junction, we have two long-term rain gauges in the Grand Valley. One's over on the National Monument, one's over at the airport. That's a huge area to cover. There's a lot of difference there. And so what we're seeing here is a bias in measurements based on like where we have rain gauges and where actual rainfall is. So if we have a rain gauge network across the country, we can estimate average rainfall by, here's a point, here's a point. Let's interpolate across the country. But where we have sparse data, where we have really strong gradients, and we'll talk about kind of uncertainty in rain gauge measurements in a minute, we can actually under or overestimate rainfall. And so in this case, it looks like we're underestimating rainfall, especially in the West, where we have a lot of mountains and really big gradients in rainfall and precipitation estimates. And this is where it's also most important to know how much precipitation is falling, because This is the Rocky Mountains. So we can get rainfall data from a number of sources: NOAA, National Oceanic Atmospheric Association Administration, and they maintain an online database of long-term rain gauges. Those of them are at airports. The airports have weather stations on them. But in Colorado, we've got, or sorry, in the Great Valley, we've got two. I've got one pulled up here. Here's the link, and we can access the data over time. So we have hourly data, we have daily data, that kind of thing. And it could go back for many years. So we'll use a data set for the homework 2 that goes back, I think, 100 years, just daily data. But more recently, we have hourly. Here's COCORAS. This is, so here's the acronym of the Community Collaborative Rain, Hail, and Snow Network. And this is a community science, citizen science type of thing. Started at Colorado State University. It's national. And basically, you can put this up in your backyard. I've got one of them. And every day you log in when you can. You're not signing a contract, you're not getting paid. And you put your information in. This way we kind of extend the network of rain gauges. Not everyone's going to report every day, but if you pull this up for the Grand Valley, there's probably a couple dozen rain gauges that we have. So it's just a nice additional data source that kind of fills in the government network. We also have early warning systems, and these are becoming more and more common as we have wildfires and burn scars and post-fire flooding. This is a graphic of a rain gauge that's also a stream gauge that Fort Collins has a network of these installed, or Larimer County, to forecast or to have an early warning system for flash floods. So Spring Creek flood happened, I believe, in '96, and for a number of reasons, not just because of the intense rainfall, but infrastructure and poor floodplain management. I think about half a dozen people died in a trailer park that got flooded because of those floods. So Fort Collins and Larimer County have done a lot of work to get early warning systems. If all of a sudden you get an inch of rain in 10 minutes, there's these thresholds that they'll make and then report this out. So you get a text message or something like that from a system like this. And here's that network. And we've got some rain gauges and foothills. They've added a bunch. We have the Cooter Canyon because of the High Park and Cameron Peak burn scars. Did anyone hear about the Black Hollow flood that happens? This is a tributary on the Cooter. It's a little community that lives there, and I think it was 21, so last year, they got a big rainfall event in the burn scar, and a few people died in that because of all the debris flows and flooding, timber that came down. It's pretty catastrophic. So these kinds of systems are trying to give people warnings. Here's a Boulder text message that you can get that shows areas where the flash flood could occur and areas that are just susceptible to debris flows and the like. The USGS has also recently been installing rain gauges, for similar reasons. So they installed a bunch right up here. Does anyone know what's going on here? Glenwood Canyon. So that's the Grizzly Creek burn scar. All these dots are hard to see. USGS represents their data by color scheme based on the quantile of rain that's happening in a certain area. Usually it's stream flow, that's what they're used to. And so all these aren't really showing anything because it's not raining right now. So, that's why they're gray. But this is a relatively new network, maybe in the last decade, if they started to install and maintain these things. You can get really high resolution data there too. All right, so we can measure rainfall on the ground. So it's pretty good. But as you can see, this network is really sparse. So we can also use radar to fill in the gaps, and radar weather stations, you've seen this when you turn on the news and look at weather, and it works by essentially bouncing radio waves off of water droplets. And we can track where the storms are going. We can also track how much precipitation is in the storm. So there's a lot of science behind that, obviously. Water reflects radio waves. Have you ever tried to listen to the radio underwater? doesn't work. I don't know, maybe it does. I don't think it does. I've never tried. But what we see here is a relationship between energy, so the energy that would come back from the radio wave and droplet size. And there's this kind of distribution of oh, sorry, this is, okay, no, sorry, this is numbers, so count of droplets or size. And so we can use kind of this information about different kinds of storms and the size of droplets to then understand the volume of water or depth of water in a particular storm. Obviously, I'm not going to be able to explain that super well, but it works, and it's not perfect, but we can get pretty good estimates of the water content and rainfall coming down outside of clouds. And then we can, of course, calibrate that to ground-based observations over time. So next generation radar or something like that, we have continental coverage of that. And so we can stitch together based on, there's a station up on the mesa, a little radar station on the mesa. We've got stations kind of dotted across the state and the country, and then we can stitch that all together with some help with satellite information to give us our rainfall estimates across the country. And a lot of scientists will use these data to go back and just be like, okay, the storm happened, let's figure out kind of like, let's track it. We can model where rainfall fell over a watershed and try to recreate some of the floods that happened. We do have satellite observations. It's pretty coarse scale, but it's the same concept using radar. When you see these hurricane tracks out in the Gulf or the Atlantic Ocean, that's based on satellite data. So just some of the options we have for estimating precipitation. But I want to talk a little bit more about this variability and uncertainty in rainfall depth. And I want you all to think about what would contribute, if I have this sparse network of ground-based observations, what would contribute to uncertainty or variability? I've got rain gauges scattered across the county, and I want to estimate average precipitation for the county or a watershed or something like that. Obviously, there's going to be some uncertainty. It's not going to be an estimate, but what are the things that we would imagine based on what we know about precipitation processes that would contribute to uncertainty, kind of spatial uncertainty? If I'm measuring it here, I want to say this represents this watershed of 10 square miles. What's the uncertainty associated with that? What's driving that? Topography, how's that going to play out? Yeah, so topography is really important. We just learned last time that elevation gradients strongly influence precipitation because of the orographic effect. And so if we look at the Grand Mesa, then we can see how this is just average precipitation. If we go up, we're getting more precipitation. And so if I want to say a watershed that comes off of, say, Cannon Creek watershed right here, I want to say, I want to estimate the average precipitation over the year or for a storm event. And I just have one rain gauge here, I'm missing out this gradient. And so there's probably going to be more rainfall for a particular storm event and on average across the year. So I would need a network of rain gauges to account for that. So a rain gauge is really only so good in estimating rainfall for a particular area, as long as that area is homogeneous topographically. You might want to think about storm tracks. We know storms kind of come this way across the valley. Is my rain gauge accurately estimating that? So topographic gradients are really important. And then smaller, shorter duration storms. So something I always see this in the summer and the monsoon season is really big storms that kind of come around the mesa and nail Palisade. So really small, really intense. Over here, sun's out. So smaller, shorter duration, more intense storms are going to be more spatially variable. We would need lots of them over an area to better estimate rainfall depth. We'll talk about duration in a little bit, but as duration shortens for a particular storm, and if we're designing something based on a shorter duration, that data is going to be more variable versus a longer duration storm, which typically has a larger area. So how can we reduce uncertainty in space? If we are really interested in short, intense storms, we need more data. What's this thing we can do to address uncertainty related to space? What do you think, Lauren? More rain gauges, more data. That's a scientific question or scientific answer. Scientists always want more data. And then uncertainty in time. That's the other thing. We've got these time series. Is what's been happening in the past representative now or not? Ideally, we can't go back in time and start rain gauges, more rain gauges, but having them and keeping them, maintaining the time series is really important so that we can see trends and that we can have, for a very highly variable phenomenon, the more data we have, the better certainty we can have on our estimates. I'm going to introduce this now. We'll talk about it again later, but this is a curve, and we're going to be using lots of curves for hydrologic design that represents, we have area on the x-axis and the percent of point precipitation on the y-axis. And the idea here is if we have a rain gauge that gives us data and we're going to do some analysis on it. So we'll be using, for example, the rain gauge over at the airport. We're going to estimate the 1% annual exceedance probability, 24-hour duration, rainfall depth. And that number is based on that one rain gauge. But we just talked about how storms are variable in space and time. And what we're measuring at one point isn't necessarily representative of what happens over an entire watershed. So if we're designing a runway out at the airport and it's going to be based on some drainage that goes up into the book cliffs that has a drainage of, say, 10 square miles, then I'm going to need to take that point estimate. So 100% of that point estimate, let's just say the 24-hour 1% storm, it has a depth of 2 inches. What this curve allows me to do is then adjust that, which essentially reduces it based on the drainage area. So if I'm extrapolating out from a point, 0 square miles to 10 square miles, then I'm going to reduce that value measured at the point just a little bit. And the reason for that is as what falls over a point is typically less than what falls over the entire watershed. And as we go farther out into the drainage area, this obviously is very big in terms of scale. What we measure at a point becomes less and less what would fall over a whole watershed. So there's many different durations here, and we'll talk about why we think of rainfall in terms of duration. How much rainfall can fall in 15 minutes, an hour, 6 hours, 24 hours. Those are different design considerations. If you think about designing a road, we are interested, what duration do you think we'd be interested in? Jesse, I'll throw that to you. Of rainfall, what duration of a rainfall event would we be interested in designing, for example, the road crown slope?
I think we're looking at right now, rainfall is like 10 year storm is pretty common. I just want to make sure that your 100-year storm doesn't flood the road by more than like a foot or something.
So that's a frequency. That's a probability of a storm happening in a given year, or given year. But think about the duration of the storm event. So it started raining, this July. I don't know how much fell, right? But how long did that storm last? That flooded the city.
Not very long.
Was it like an hour, 2 hours?
Probably.
Okay. So if we think about like the 1 hour storm event, super intense, right? That is what we might think about the duration of a storm for designing our culverts, the slope on the roads, that kind of thing. So if we want to avoid flooding for a particular duration. If we think about a longer duration event, maybe that's something that would result in a river flood or something like that, right? So different durations are going to have different design applications. And what you can see here is as we decrease the duration of the storm event, we dramatically decrease the percent of what we estimated at the point. So the rain gauge told us the 24-hour. Well, if we go down, and we'll say the 1 hour now. 1% chance duration storm is 1 inch. Now we're gonna go to 10 miles. We're gonna reduce it by much more because those smaller storm or those shorter duration storms are typically smaller storms. So if we have a drainage area of 10 square miles, maybe I should draw this up on the board. Actually, I can draw it up here. Okay, so if this is our watershed, and we've got a storm event that comes in, and it's a 1 hour duration, then that storm event might just cover, it might just kind of go this way, right? And here's our rain gauge right here. 1 hour storm. So it's usually smaller, it's intense, it moves more quickly because it's just 1 hour. Whereas if we had a storm event that was our 24-hour, what's that going to look like, do you think? A storm event that lasts for 24 hours or longer. It could be the entire valley. Maybe it's like this is what the storm looks like, right? And it's moving slowly in this direction, but it's lasting a lot longer, it's bigger, and so it's going to be more uniform. All right, and that's why we have these, just drag this up, area reduction curves, and we'll use this in our modeling, and we'll use this on homeworks and maybe even the exam. So we need to understand that shorter duration storms, more variable. What we measure at a point for them, when we apply that rainfall depth for a whole watershed, we're gonna reduce it more than we would for a longer duration storm. So on the ground gauges, stream gauges, or precipitation gauges will always be the most quote unquote accurate measurement of precipitation because it's just what fell on the ground. Of course, they have their own challenges. They're not going to be going away anytime soon. And we need them to calibrate and validate our estimates from ground and space-based radar estimates of precipitation. They're really good at measuring what's in the cloud, but translating that to what falls into the ground it can be challenging. So when we use rainfall data, it's good to not rely on one gauge's data. Having a network of gauges, multiple sources of information was important. And typically we're going to be getting our design information from maps like this. These maps were generated from rain gauge networks. Maybe they're supplemented with radar rainfall data. And I've got one for the front range area. And this is a map that shows the depth that fell over 7 days in 2013 on the front range for that flood event. And it's showing contours and colors. You can see, much like the topographic contours, these are rainfall contours, and this is called an isohydral map. So iso, the same, hydral, that's that rainfall word. I don't know if that's Latin or something like that. So a rainfall contour is called an isohydral. It's a weird word. That's a rainfall depth contour. And we make these through interpolating. So we've got depths at points, and then we can interpolate that and make contours. So here is an exercise we can do to estimate this. And I'm going to walk through it, and I'll save the activity till the end of the lecture so we can hopefully have some time to do that. There's a couple different considerations we can make to estimate rainfall, either at a point or across a whole watershed. So if this is a watershed, we've got 4 rain gauges on it. They measure these depths for a particular storm. And one of the problems we might be interested in is estimating the rainfall depth at this point at a lot scale, something like that. And if we wanted to do that, then we can use a method called inverse distance weighting. And what that does is it takes information from each point, it attributes it to the point we're interested in, and then it weights it based on the distance. And so we can calculate the distance just using Pythagorean theorem. So we can estimate the distance, and then we can use different powers here, but we can create a weighting factor, 1 over d squared in this case. And then we can estimate the precipitation by taking the sum of the individual precipitation gauge measurements multiplied by the weights for each distance, and then dividing by the total sum of weights. And so that'll give us the, in this case, inverse distance squared estimate of rainfall at that particular point. Now that's for a point. If we're interested in an area, we can take the same information and create our own contours, our own isohedral map. We can do that by using linear interpolation. What this shows is we're connecting the incremental data. So it's kind of simplified here in whole inches. So we just draw a line. You can just do this by hand. You don't have to do any calculations here. And we're going to connect the dots here. So 3 to 4. We'll put the midway point at 3.5. Same here. We're going 3 to 5. So we put these 1/2 inch midway points. And then we're just going to connect those depths that are equal with lines. We'll just draw lines through them. Do your best to draw by hand. And then we'll note that the area in between here will sign whatever the average is between those. In this case, 4.25 inches between 4 and 4.5 inches. This is just a manual linear interpolation method. It's very similar to the kind of computerized method that you'll see on those and that isohedral map we saw previously. So once you do that, you now have your isohedral map. You've made those contours, and then you can take the area and get an area average precipitation estimate for the whole basin. So this is our watershed. We can take the individual areas, multiply them by the average rainfall in each one. So this would be 4.25, 4.75, 5.25, and then do the sum of the individual areas times the individual precipitation estimates divided by the sum of the areas. And that will give you the area average precipitation. All right, so we'll take a quick break there.